Hi, Joe, chemistry teacher again. I've got 4 problems using the named gas laws that we've seen recently and previously. And well, let's just plow right into it. It'll tell you, I'm not going to tell you which equation we're going to use, which law it is. We'll figure that out as we go. So the first one, number 1, says at 25 degrees Celsius, a sample of gas has a volume of 2 liters. What will the volume be if the temperature increases to 50 degrees Celsius? Pressure and amount, not changing. So the first thing I always have my students do is we make a list of everything we know from the problem. So I got 25 degrees Celsius, that is a temperature. A sample of gas has a volume of 2 liters. So volume. What will be the volume if the temperature increases to 50 degrees Celsius? Now, we've got 2 temperatures and 2 volumes, and we need to keep track of which one's which. So the first one that I came across I will call T1 and V1, and the other 2 I'll call T2 and V2. That kind of tells us which equation we want to use, right? If we've got T's and V's, we're going to use Charles' law. And we've got to make one adjustment before we begin. These temperatures are in Celsius, and that's a no-no. We must put those in Kelvin. How do we do that? We add 273. Now we're ready to plug in. Now there's a couple of ways you can do this. You can plug in the numbers and then rearrange and do the algebra, or you can do the algebra first and then plug in the numbers. I kind of like moving V's and T's better than I like moving 323s and 298s and all that stuff. So I like to do the algebra before I do the math, if that makes sense. So I'm looking for V2, so I need to solve this for V2, so I need to multiply both sides by T2 in order to make that happen. And after I multiply both sides by T2, the T2s are going to cancel on this side, and we'll be adding it to the top on that side. So now we're ready to plug in. V1, 2 liters. T2 over T1. And I like to line it up so that I can tell pretty quickly what's going to cancel. That I have misplaced my calculator. There it is. I'm ready to do the math. 2 times 323 divided by 298 equals 2.16778. We got 2 digits here. Let's go. Oh, that was 2.00. Sorry. So there are 3 digits there. 3 digits all the way around, 2.17. And the only thing that didn't cancel was liters. You need to put your units on and cancel them and show your teacher that you know what you're doing, because that will make them feel much better about you if they know that you know what you're doing. All right, number 2. Oh, by the way, that was Charles' law, right? Charles' law. We're letting the problem tell us which law to use. The gas has a volume of 5 liters. When the pressure is 133 kPa and the temperature is 290 Kelvin. That was nice, it's already in Kelvin. At what temperature? Oh, now we've got another temperature. At what temperature will the volume be 6 liters and the pressure be 150 kPa? And just a word on significant figures, since there's a decimal point on the 290 and the 150, those are 3 significant figures. Those are 3 significant figures. Everything's 3. We'll probably end up with 3 in our answer, just for what it's worth. So the equation, we've got V and P and T, so we want V and P on top and T on the bottom. Now we've got the we got, this is the combined law, right? And we're in the right form. We're looking for the new temperature. So what I like to do on a problem like this, don't know what math people or your actual teacher might think, I just want to do the reciprocal of both sides. T1 over V1 P1 equals T2 over V2 P2. Now it's easier to solve for T2. I just need to multiply both sides by V2 P2. Those cancel. T2 equals V2 P2 T1 over V1 P1. I'm ready to plug in. V2, 6 liters. P2, 150 kPa. And T1, oops, 290 K over V1 and P1. Now my kPAs are going to cancel, my liters are going to be canceled. I'm left with Kelvin. Seems reasonable. 6 times 150 times 290 divided by 5 divided by 133. I get 392 Kelvin. Sometimes if you don't do it right, you might get an answer like that. 0.0025478, which means if that's a Kelvin temperature, that is really small, and you've probably done the problem upside down. You've probably solved for 1 over T2, and your calculator has a button that will fix that for you. At least mine does. It's the 1 over X button right here. Yours may say X to the minus 1. And if I hit that, look, I got 392. So if you get a really crazy small decimal number for temperature, you've probably got the reciprocal of temperature, just something I learned over the years. So we got 2 more problems that we can do in this set. So we've seen a Charles law and a combined law. Let's see what this one might be if we get our camera back into focus. There we go. So here's number 3. A gas at 303 Kelvin, well that's temperature, occupies a volume of 12.5 liters at a pressure of 95 kPa. What is the amount? Amount is N. Might say what's the number of moles, what have you. I only have 1 of everything this time. So notice on the first problem, I had 2 T's and 2 V's. On the second problem, I had 2 P's, V's, and T's. Oops, right around there. P's, V's, and T's. I only got 1 of everything this time, which tells me that I'm going to use this equation, which is the ideal equation. Okay, so I still don't have a value. It didn't tell me in the problem what R was, but we know what R is. R is 8.31 liter kPa per mole Kelvin, because it's R. So let's plug in. Oh, we need to rearrange. We're looking for N, so N would be, right, I'm going to divide both sides by RT. I'm assuming you have some algebra skills. PV over RT. So let's just plug in N equals P, 95, V over R and T. Now let's look what happens here. I have kPAs in the top, I have kPAs in the bottom. I have liters on the top, I have liters in the bottom. Sorry about that. I've got Kelvin in the denominator of the denominator. I've got Kelvin in the numerator of the denominator, so those kelvins cancel, which leaves me, my unit would be 1 over moles, which will just be moles, this moles, and the denominator of the denominator is coming up to the numerator. We'll plug in the numbers here. 95 times 12.5 divided by 8.31 divided by 303, 0.4716. We need, look, I got 3, I got 3, I got 3, I got 3. I need 3 digits in my answer. 0.472. Okay, we got one more problem, and we'll be done. So the diver's lungs will hold 3 liters of air. Sorry, the kids are coming in. School's about ready to start. He inhales a full 3 liters at the surface where the pressure is 100 kPa, and then dives to a depth where the new pressure is 200 kPa. What will be the volume of his lungs at the bottom? Well, it's P's and V's. And we want V2, so we're going to divide both sides by P2. So V2, P1, V1 over P2 equals, let's say P1, 100. V1, 3. P2. Cancel what'll cancel. That's a half of 3. Oops, I was not showing you very good here. I canceled everything. I've got 1/2 times 3, which would be 1.5 liters. So when the pressure doubled, lungs volume cut in half. This is Boyle's. Imagine going the other way. If you start at the 200 kPa depth with a full 3 liters and you rise to the surface, it's going to double. Your lungs are going to go from 3 to 6 liters. I suspect they're going to explode at that point, which would not be healthy to have your lungs exploding. So, hope this has been helpful. Again, use the problem, let the problem dictate what formula you're using. See you next time.